Okay, very good. This one. Perfect. Okay, so good afternoon, ladies and gentlemen. I have the pleasure to introduce Pei Su from Nečas University, and she did her PhD in University of Bordeaux. From supervisor was Professor Tucnak and
David Lam.
yeah, and who?
David Lam.
And the second one, sorry. And anyway, she is speaking about the asymptotic analysis of the system describing a small body in viscous incompressible folds. Please.
Thank you very much. Thanks for Shaka and all the organizers. And I have a chance to present a work with my friend. Today I discuss something about a small rigid body immersed in a viscous incompressible fluid. So when the NS coupled with another equation, it's very natural to ask if this coupled relation change the NS property a lot. Or in other words, if this coupled system inherits some property of Navier-Stokes equation. If yes, in which situation and how? And today we are interested in the case that the body is small. The size is described by the parameter epsilon is small, and we would like to describe the dynamics when the rigid body shrinks to a massless point. And this is the first time for me to work on this immersed case. And it's a joint work with Jochen from University Bakisakle in Oxford.
Try once the computer just next page on the component. Work.
Doesn't work.
If you click on the slides once. Okay. Click on the slides once with the mouse.
Okay, this is my this is the content, the outline of my presentation. Firstly, we get into the program setting and we introduce the governing equation of this coupled model, and we introduce the concept of the Leray-Hopf solution and some related results on this asymptotic analysis topic. And then we try to reformulate this model in the abstract differential equation because we want to get some uniform estimate for the solid velocities, and which would play an important role in the construction of the text function. And we will try to develop some this way to the back maybe. So we will try to develop some decay estimates about the C group associated by this with the scrap operator, and then based on this decay estimate, we construct a test function, and then use the default argument to obtain the solid velocity estimate. And finally, based on this about estimates, we construct the approximate test function sequence which will be admissible test function for fluid structure system. And then to deal with the nonlinear term, we need a local strong convergence. And finally, we are able to pass to the limit from the fluid solid system to the pure fluid equation. So now this is the program setting. We consider the incompressible fluid as viscous as a homogeneous fluid. It interacts with a rigid body, which in particular assume it is the ball with its centered at h epsilon t, with the radius epsilon and occupied area, which is this ball is denoted by s epsilon t. And the fluid domain is at exterior part of this S epsilon is denoted by curl F epsilon. And we have some notation. This N is the unit normal vector of this this ball. It directs towards the inside of this solid domain and independent of epsilon. It's a ball, so it's independent of epsilon. And the fluid density is the U epsilon F without loss of generality. We assume it's 1. And most important, we assume that the solid density is also a constant. And the U epsilon is the velocity of the fluid, and the P epsilon is the pressure in the fluid. M epsilon is the mass of the body, and the omega epsilon is the angular velocity, and the G epsilon is the inertial tensor of the body. And this is the system describing the fluid respiratory action. And the fluid is described by the incompressible Navier-Stokes equation. And there are two equations describe how they come. And it's a conservation of the linear and the angular momentum. And also at the boundary, the velocity of the fluid is consistent with the velocity of the body. And to close the system, we propose some initial data. And in this equation, we can see the fluid and the solid coupled by the conservation law equation and the boundary condition. And the sigma is the Cauchy-Sweat tensor. Is du is the deformation tensor. So you know very well than me, I think. So this P is the pressure. And now in the asymptotic analysis parts, it's very important to capture the motion of the body, which is very important to construct the test function. So firstly, let us see what we can obtain from the energy estimate. So we take in the product of the fluid equation with U epsilon, and then integration by parts, use the coupled condition at the same time. And then we have the following energy estimate. It's given by the L2 norm of U epsilon plus the second term is on the translation velocity of the body. M epsilon times the H dot epsilon squared plus the inertial tensor term and the L2 norm of the deformation tensor, which is bounded by this initial data. So from this energy estimate, what we can say is the because this inertial tensor is positive, so we can obtain some. If the initial data is bounded, the right side is bounded, and then we have the uniform bounded of this translation velocity, which gives us M epsilon H dot epsilon square is bounded. But if the signs goes to 0, the mass also goes to 0. This observation doesn't help us. So what we can do? So for this issue, people doing some assumptions related to the density of the body. For example, they assume that M epsilon minus y½ goes to infinity in 3D, for instance. So what does it mean? So M epsilon times epsilon minus y½ goes to infinity in 3D. So we read that this M epsilon 0 epsilon 3 times epsilon minus y½ is real epsilon times epsilon 5/2. This goes to infinity. So it means that this density rho depends on epsilon in this way. This power alpha is at least strictly less than -5/2. So the same that when epsilon goes to 0, the density goes to infinity. And how to use this together with the energy estimate, we have the M epsilon Leray-Hopf H dot epsilon. This is bounded. If we have this information and it will give us rho epsilon Leray-Hopf epsilon we have H epsilon dot. This is the bounded. And then we have epsilon 3 plus alpha over 2 H epsilon dot. This is bounded. This is the key points to use in the estimate process. And with this kind of condition, you can even prove that you can justify the limit without small data and also for arbitrary shape. But with this kind of condition, if you just need this body is included in a ball with arbitrary shape in a ball with radius epsilon, and also if it shrinks in does not shrink in asymptotic way. So this condition is stronger, simply saying that the density goes to infinity. But it makes difference in the estimate. So now we have some related work with a quite hot topic in recent years. They studied by Shaka and Perez and many other experts in this area. And first, there are many works and with various conditions on the fluid and also on the body, on the parameters of the body, because of this kind of problem. Firstly, for the fixed body, so the body is fixed in the domain, and the assumption is usually about the initial vorticity and the circulation of the velocity around the body. And firstly, Iftim is a professor in University of Lyon, and he and his collaborators studied the case, the limits of program in 2D and 3D with this kind of condition. And then his PhD student, Christophe Lacaille, he studied the thin obstacle tending to a curve in the fluid. And he saw the 2D case in 2010 and for the 3D case in 2015. And if the body can move in the fluid under the influence of the fluid, the situation becomes much more complicated. You need to do something like this or control the velocity of the body. And firstly, Leray-Hopf and Takashi, they consider 2D case. It's a disk in the fluid, and they just find the limit, but in particular, the density is a constant. It does not change with respect to the size of the body. And then her and Iftim, they studied based on this very similar assumption. They justify the limit in 3D also, but with large density assumption. And then with the very similar strategy, there are some also other work coming. For example, Marco Brown and Shaka, they studied also maybe 3D. They proved that with this kind of assumption, the fluid cannot accelerate the body. It's very natural because the body is too heavy in the fluid. It's a very natural result. And then Ferrez also studied the incompressible, it's not homogeneous incompressible fluid. And their assumption is also related density, but it allows the density of the solid asymptotically small. So what we do here, and also there are some compressible cases is solved by Shaka and Further. We are not interested here. We are not going to the details for compressible case. And what we do here, and we consider the 3D case with constant density. So normally, if you want to know some parameter, how does this parameter influence the coupled system? It's very reasonable and effective to use the control variable approach. It means that you just change this parameter, you keep other things constant, you see what will happen. So now that's why we consider this constant density case in 3D. So now we introduce the Leray-Hopf solution. We call that this three things function is a global Leray-Hopf solution of if for every time t u is at infinity at 2 cap at 2h1 is very classical, and in the solid domain u is the translation velocity plus omega across the distance y minus h epsilon, and you verify this equality is very natural to see it's a weak solution. And this test function say the deformation tensor vanishes in the solid part. And there are some references for the existence of this Leray-Hopf solution. For example, the Denis and Marius, their results. You cannot find exact this model, but it can be derived combined this kind of reference. The results say that there exists at least one global Leray-Hopf solution for this kind of fluid structure problem with assumption on the initial data. And then we found that we can do a change of variable to rewrite the system in a spatial fixed domain. So it's like you pull back the body to the initial time, but it still rotates. It can still rotate. So you define a new variable where is x plus h epsilon, and the v epsilon is u with the space x plus h epsilon, and we denote the translation velocity with a new function is L epsilon is h epsilon dot. And then with this kind of change of variables, the system becomes this number two system. You can see here we have a new nonlinear term. It's the L epsilon dot gradient V epsilon. It's kind of rotation term appear. So this is also the main point. That's why we need this solid is a ball, because it's related to the fixed point argument. And then we want to derive the solid velocity estimate, and then we need to define the extension every function to the whole space R3. And we ask the initial data satisfy this basic assumption. And we extend the velocity and the density to R3. With the V, capital V is extended version of the velocity. It includes the three components. It's V, L, omega. So we extend in this way. We define it's in the solid part is L epsilon plus omega cross x, and for this L6 for V is in L sigma Q. when every function at a Q space with divergence free condition and also the deformation tensor vanishes. For this, in the solid domain, if you have this deformation tensor vanishes condition, you can find the unique pair at omega such that this U is exactly L plus omega cross X. So it means that this extension makes sense, not only formally. And also now with this initial condition assumption, you can not difficult to verify that this extended initial data with this L2 as divergence free. And also it's not difficult to derive the relation between them. And this small v is the fluid velocity is this extended version and now we want to reformulate the system in the abstract form. We define this space X epsilon Q. X epsilon Q is defined in this way. It included three components. We assume that it's by L omega phase in LQ and the other two in R3 space. That is a divergence phase 0 in the fluid domain. And the phi and L plus omega cross X, they are consistent in the normal direction. As we have already mentioned on last page, if you have the deformation tensor vanishes, it means that this space is actually equivalent to the L sigma Q space with the vanishing deformation tensor. And then the norm is defined by this the sum of these three parts. And then according to results by Wang and Xin in 2011, they show that this LQ space can be divided into three parts. The first part is described by this exactly this X, capital X epsilon Q, and the other two parts is given by two potential forms. It's like grading something. So, and then we define the projection operator. This P epsilon is from the LQ to this capital X epsilon Q. So you may notice that this projection operator is actually a spatial part, Leray projection. With additional condition, the little difference, only difference is with additional condition is the deformation tensor vanishes in the solid domain S epsilon 0. And then we define the fluid structure operator. Firstly, we define the curl A epsilon Q. The domain is a formula you can write the equation into this into the evolution equation, and then you say you will have the definition of this curl A epsilon. But you can see here we do not have the pressure. We do not have the pressure because in the integration, you just need to take integration by parts, and then you will have the grading in the integration because we use the projection operator, so it will disappear finally. So this epsilon V is divided in this way, and the domain of this epsilon Q is the W1Q cap this state space X epsilon Q, and especially we ask this is W2Q for every Q between 1 and infinity because there's a Laplace operator. And then we define the fluid structure operators through a projection operator applied to this curl A epsilon. Because everything you are discussing is on the state space, you have to projection or everything into the state space X epsilon Q. And then according to a very recent result by Silva and Martusnak in 2022, they proved this fluid structure operator actually indeed generates a bounded analytic semigroup on the state space X epsilon Q. So which give us the chance to rewrite the system in this kind of abstract form. We use the extension of the velocity capital V is 3 components, do not forget. And then we can rewrite the fluid structure system in this abstract differential equation. The right side is the projection divergence F epsilon V. And F epsilon V is divided in the 2 parts. In the fluid is this cross, and in the solid part is 0. And with the initial data, V epsilon 0. And from this form, it's directly to formally write the formula for this abstract differential equation. It's by using the Duhamel principle is given by V epsilon is a semigroup with the initial data plus the convection of the semigroup with this self-term. Now, if we want to prove it's indeed a solution of fluid stress system, we need to use the fixed point argument. But how to prove it? The main tool is the LP-LQ estimate of this fluid stress operator. So that's the main tool to proceed the fixed point argument. The result is given by these 4 key C's, and the first 2 is the estimate to the semigroup directly. The first one is for P is finite, the second case is P equals infinity, and the third one is to estimate this T, the semigroup applied to the projection divergence operator. And for this kind of F, and the last one is to estimate the gradient of the semigroup. And this proof for fixed epsilon has been done by the last reference. And we have to notice every time when you use this estimate to you have to verify which kind of F you are considering. You have to say which kind of Q, and R is what is R, and you determine the what is P. It's very important. It's different with the 2D case. And what is worth noting that this estimates holds for arbitrary shape, because you can see it's only related to the linearized model. So for fixed epsilon, the estimate holds for arbitrary shape. And then what we do here is just to verify this kind of estimate is epsilon invariant. So it means that you have to prove the constant on last page. The constant of C1, C2, C4 is invariant when you change the size of the body. So in general, we just use the scaling. We define the x theta is x over epsilon, t theta is t over epsilon square, and the mu of V1, the pi 1, and V1 omega is depends on these new variables, and with our assumption of the density is constant. So we have m epsilon is epsilon cube m1, and this inertial tensor is epsilon 5 g1. So with this kind of scaling, it's not difficult to verify that the linear system is epsilon invariant. And finally, we have to notice the last estimate is not directly to use the linearized system. So it's the gradient TT epsilon Q. But here we employ a duality argument to use the semigroup TQ, the dual is T epsilon Q prime. Q prime is the conjugate of Q, and then you just use this dual argument. In this case, we'll go back to the third case directly. And then when you can, so if up to now we are sure that we can use that as a P-value estimate to this shrinking limit problem. And this is the existence of the Meld solution for every initial data in the L2 cap L3 with other condition in the state space, and we ask this with initial data in these two space is small, and there exists a solution V epsilon is given by that Duhamel principle, and it's indeed satisfied the fluid structure problem, and also especially we have this velocity estimate with for p between 2 and infinity, it can equal to infinity, and with the power 3 over half and 1/2 minus 1 over p. So you may ask the question that you do something about Meld solution. So how do you use it to the Leray-Hopf solution? So this is a good question, and actually the Meld solution is a weak solution. You can the strategy is actually given by paper by Takashi 2004. It's given by 2D, but it's also okay. You can construct a regular initial data V epsilon N0 in the domain of the 1/2 operator, and then you ask this initial sequence converges to the initial data V epsilon 0. And then you also ask this initial sequence satisfy the condition for the Meld solution. And then for every initial this kind of initial data, you have the solution for the fluid structure. You have the solution V epsilon N, and you can prove this solution sequence convergence to a Leray-Hopf solution. And in other hand, and you can use the sensitivity of this solutions sequence to the initial data. You can prove this actually this sequence V epsilon N convergence to Meld solution, which is very clear. You can see during the fixed point procedure. And up to a subsequence, you can show that there is a subsequence convergence to a Leray solution and also convergence to weak Meld solution. Actually, you can show that the Meld solution is the weak solution. And then this is the fixed point argument. You can to start the fixed point, you have to have the operator, and also you need a domain. And we define this domain is epsilon. Now we start from the initial data in the F3 space. You define the space is the K epsilon for this extended version of velocity, and then you ask the additional condition in the T1/4 V in the continuous and in X6. T1/2 V in the C in X infinity with additional this minimum of T1/2 1 gradient with all the conditions to finish the fixed point procedure. And with the norm, the summation of these 3 parts. And then you define operator lambda. Lambda epsilon is exactly the Duhamel formula. And then we use the LPIQ estimate. We are able to show that actually this map lambda epsilon is a contraction mapping in a ball with radius r, which depends on some constant in the LPIQ estimate. And especially we have this the norm of this velocity v can be controlled by the initial data in the X3 space. So it's not enough for us because our Leray solution is in L2 space. You feel something in L3. So we need to connect this to the L2 space. And then now we consider this initial data further in the L2 space, where L2 cap L3 with other condition. And then we can show that this V epsilon is actually at infinity at epsilon 2. And the T3 force V is in infinity at X infinity epsilon. And then you can use the interpolation theory to derive that the general decay result. So how to use this? From here, you see that we have remember that this we include the 3 components. The second component is our translation velocity, which is what we want. L is in the second component. We have the from this T3 force, we have the estimate for this translation velocity. We have the T3 force H dot is bounded in the by this mu 0. And then you realize that this H epsilon sequence is bounded in W1Q for this Q between 1 and 4 over 3. And then with companies, you have the convergence of this H epsilon and with the limit in W1Q space. And also, you notice that this H epsilon is uniformly bounded in the interval 0 to t. And also by using the Atlas Colli, you have the strong convergence of this H epsilon. So from here, you see that finally, when the size go to 0, very small in some sense, and the body will go to the neighborhood of a ball centered by this limit H. So now we based on this limit, we construct the approximate test function. We define the cutoff function in this way. It says infinity is it's 0 in a ball with radius 3/2, and it's 1 in the outside of the bigger ball with radius 2, and the middle is smooth. And then with the scaling, you move the center to H, the limit you get before. You move this to the limits with the center at the limit, and then at this you can verify this new cutoff function at K epsilon satisfies the property. K epsilon is W1Q because it depends on H, the regularity of the time inherent from this limit H, and for space it's smooth, a Q between 0 and 4 over 3. And for every T, you can see directly it's 0 in a ball with radius 3 over 2. And also you have the basic estimate for this K. And then you will use this estimates to construct the approximate test function sequence. And then with this cutoff in hand, we define this phi theta is given by this phi th plus epsilon y dot this gradient K. And this with this phi theta, you can verify this phi theta satisfies 0 mean condition. So you start from this divergence problem for the south term satisfies 0 mean condition. There exists one solution for the G theta epsilon with the regularity for time is W1Q, and for space is H10. And this omega 1 is the null constant part of the cutoff. It's the smooth part. And then you found from phi theta, you found the G theta epsilon. And with the G theta epsilon, you define this phi epsilon in this way. The phi epsilon is a phi this new phi times K epsilon minus this G tilde epsilon with the scaling. And then you found you can use this new phi epsilon to approximate every CC infinity function with divergence free condition. And then you prove that this new phi epsilon is divergence free and it vanishes in the ball centered at the limit position H with a radius 3½ epsilon. And in particular, you have a strong convergence to this phi epsilon converge strongly for time also, which is also a very different part with 2D case. In 2D, they just have the weak convergence. And then to deal with the nonlinear term, we need some strong convergence to go through the nonlinear part. And here we construct very similarly, but here phi is just depends on the space variable. So you define this phi epsilon is phi K epsilon minus G epsilon, and then you define the map on H2. It's from this phi to this integration. The integration of U epsilon dot phi epsilon. And then you verify this map is linear continuous in H2 space. And the Lax-Milgram tell you that there exists a capital U in the dual space H minus 2. And then you can verify that this capital U sequence is uniformly bounded and equicontinuous. You have some convergence on this capital U. And then how to go to get something about small u. And actually, this capital U is not far from this small u epsilon. And based on the triangle argument, you have the convergence of this u epsilon. You denote the limit as u, and then you use the interpolation theory. You can get the convergence, strong convergence in this L2 space locally. So this is the convergence result, the main result, and we have the test function, and we prove that for this initial data in L2 cap L3, the divergence free with this normal condition and the initial data weakly convergence to the U0, and this small data you prove that U epsilon weakly convergence to the weak star in infinity L2 and weak in L2 H1. And this U is nothing but a solution of the Navier-Stokes equation in R3. So from this result, you see that if the body is very small, you put it in the fluid, it does not change the property of the fluid a lot. And it can be, it's very negligible in the fluid. For more details, you can see this manuscript. So, sorry. So finally, I want to do some more comments and discussion for the main technique part. So firstly, the result is stated for the constant list, but it still holds for the following case. Firstly, if the density, its density can change, but it can be bounded by constant ρ0. ρ0 is independent of epsilon. So explicitly bounded, so the same story. And the second case is that there are several bodies in the fluid without collision. The main point for this is you need a positive distance between the center of the body, each body. You need a distance for the approximate test function. And also, if the mass of the body does not change with respect to the size, it's very simple. You just need an energy estimate to do it. You don't need this IPLQ estimate. And also, I want to say that for construction of the test function, remember that we constructed the test function around the limits, of the body. For example, the here at the edge you don't see, and then you know that when which one goes there, it will go into some area centered with this limit edge. We construct a test function around this limit point, but I want to see that it's also you can also construct around this edge epsilon t. You follow the body, you don't need weight there. You follow the body, and then you know it will go there. But you follow the body, and also what we do here is you do a test function right here. You know that when epsilon come very small, in some sense it will come here. The body will come here, but it can also center the at epsilon t follow the body. So because in the proof we just need the regularity of this epsilon t. And next discussion with the results with 2D. In 2D, the approximate test function, the property is not better than 3D because it just have the weak convergence. Like how that actually they divide the convergence procedure separate in two steps. Firstly, we construct the test function with a new small magnitude, and the size of the body is still epsilon. And because they don't have the strong convergence, they just have a weak convergence. First they fix this and let epsilon goes to 0, and prove the fluid structure system with this kind of test function. It looks like Navier-Stokes, but and then firstly we send this epsilon goes to 0 with this approximate test function for fixed if, and secondly the left if with 0. And also in this process, they also need a strong convergence, but the strong convergence is in a domain depends on income. So that's for their strategy. So here we can do it together. So finally, I want to see why do we need the solid is a ball? Why this is important in this argument? As I have already mentioned firstly, this is very important to proceed the fixed point argument, because there's the rotation term in the after the change of variables. But if it's not a ball, there's some technique to deal with the problem. The arbitrary, because our change of variables is just to pull back the body to the initial state. But you can consider, you can also, when you pull back, you can also include some rotation inside. So for example, you define this kind of change of variables. When you define y is the qx plus h. Q is the rotation matrix. And also you define v and then it's the q transpose u with a space like this and L omega. What's the problem with this? You use this new change variables, you can derive the new system, but this term in red is unbounded. You're not able to control this. So maybe it's not in. So now I think there are still some work coming. But it will need some dedicated change of variables to achieve the arbitrary shift, I think. But as I know, it will coming. It's on the way. So that's what I say today.